So this video is going to be about stars, and we all are fascinated by stars. We look in the night sky and we think, oh, what's that little thing out there looking back at us? That shiny little thing like a jewel. Don't we go to our grandmas and say to them, oh, see, I see something there. Maybe it's my grandfather who passed away. Maybe it's someone who I love who is not here with me anymore. And we associate a lot of things with these little tiny objects in the night sky. But what really are they? I mean, what kind of stuff are they made of? And why do they exist? Do we think about these questions? And if we think, then maybe that's the start for all of us to swim in the world of imagination? No, of data, of astronomical data that has been collected over the last 100 years, and that has told us and that has proved that these shiny objects are no messengers of God. They are actually astronomical objects that have a lot of things going on inside them. So what is a star? So we have this basic definition, and it goes like this. You can see it on the screen. A star is a self-gravitating luminous sphere of plasma in hydrostatic and thermal equilibrium whose energy output is sustained by nuclear fusion in its interior. These may be heavy terms for people who are not from the science background or who have not studied science, but still you can imagine. You know about gravity, you know how a sphere looks, what's luminous, what's equilibrium. These are terms that we use in day-to-day language. But still, if you think you don't get the whole picture, I am here to talk about what these terms, these lines dictate. So, what is self-gravitating? Why is a star self-gravitating? Basically, a star, it's formed when we have these large clouds of gas. Actually, all the stars are made from these large clouds of gas, and some stars are made from not so large clouds of gas. So what happens is that when these large clouds of gas have these fluctuations inside them, for example, there may be an old star that died, or maybe there's a solar burst, or maybe there's a thermal expansion somewhere. So it creates certain zones inside this particular gas cloud, and these zones have more density compared to the other zones of the gas cloud. And due to this, difference in density, what happens is that there gets more mass in that particular area. Mass and density are, related. Density is mass upon volume. More the mass somewhere, more is the density. For example, a thermocol ball, is less dense than a real ball of made of steel or of some heavy item because there's more mass in it. So what happens is that in that particular area, there's more mass, there's more density, and gravity is something that's associated with mass. More the mass, more the gravity. So that's why Sun has a more gravitational pull than Earth's because it's quite massive compared to the Earth. So what happens is that these places in the gas cloud, they become more dense. Therefore, there's a gravity that makes it much more denser, because gravity attracts mass from surroundings. It means the object is structured. The object that gets formed in those gas clouds is structured by its own gravity. First, it became more dense due to certain events in the gas cloud. Then, due to becoming more dense, its gravity started to attract more matter, and therefore it became more heavy and it became more compressed. There is no external force, like for example, there are no hands that are forming these balls of stars. It's their own gravity acting on the material they are made of. And as gravity increases, it increases as you move inwards into the star's core, and it becomes more dense there because the local density is more in the center than it is in the outside of the star. So pressure is also increasing because there is more gravity, there is more pressure, there is more temperature, and there is more density. So all this mix up to create a very high density, high temperature zone inside the core of the star. And what happens when temperatures are high and this pressure is high? At certain temperatures, which are around 10 to the power 6 kelvins or more than that, more than millions of kelvins, the electrons that orbit the atoms or that are a part of the atomic structure, they get ripped off. The atomic structure itself breaks apart, and there's this soup of electrons and of other subatomic particles inside the star, and it's called a plasma. That's why we have this term, the luminous sphere of plasma. Now, why it's sphere? Why it's spherical? The star, have you ever wondered why the star is spherical? Well, there is a big reason for that, and that is because gravity acts everywhere equally. It pulls everything equally. It's very isotropic, I would say. Means it's pulling everything with the same force in the three-dimensional space. So the least energetic state is the sphere. That's why these stars or these large astronomical objects usually have a spherical. It's not exactly spherical. If it is rotating very fast or there are magnetic fields interfering, then the shape may be oblong or it may be stretched out, or there may be different areas where the radius of curvature is more compared to other areas, but generally speaking, it's quite spherical. Now, what happens is that at these large millions of kelvins, these electrons, they get stripped apart and this matter becomes fully ionized. Ionized means there's electrons floating around and soup of plasma. So what it creates the condition for fusion. Fusion is a nuclear phenomenon, and it doesn't occur everywhere. It occurs only where the temperature conditions and the pressure conditions are so enormously high that protons can combine and neutrons can combine to create a heavy atom. So hydrogen combines and forms helium, and the energy that is released is purely E is equal to mc square, and it's very, very large, huge, enormous amount of energy. And this energy that gets released inside the core, it gets released in an outward direction, from away from the core. So we can imagine the gravity pulling the star and the nuclear fission energy, it's pushing the star apart. So there comes time when there is a balance of these two, this gravity and this radiation energy and everything, the energy that's propagating out of the star, and it leads to a hydrostatic and thermal equilibrium. The term, it came from this particular idea. It's not an idea, but it's a fact. And it leads to a stable star that can run for billions and even trillions of years and remain stable due to this particular relation between gravity and internal pressure due to fission and other reactions that happen at these large temperatures and large pressure scales. So you understood a lot of things from this particular audio, that why these stars are able to sustain their structures. It's very simple. The gravity compresses the matter that comes from the gas clouds, which then raises the temperature of this particular star. It's not uniformly increasing, more in the core and less as we go outside. So high temperature and high density and high pressure situations and condition lead to fusion. Fusion generates pressure again. Well, you see the loop is going back, so pressure is also increasing. Now pressure, what this pressure does, which is produced by fusion, it pushes away the matter outside, tries to push away, and does so by resisting the gravity that is pulling the material inside. So there's a balance, which is the hydrostatic and thermal equilibrium. And the photons that are able to escape the outside of the star, and it happens in a very long time, which I will further discuss in the upcoming videos, because of certain scattering that happens inside the star. And when these photons go out of the star, they are able to travel the interstellar space and reach us conscious beings to see and imagine and wonder what great things are these, what great dots are these in the sky.